Hello everyone. I am very honored to introduce our work. In this paper, we focus on dealing with the long-tail phenomenon in trajectory prediction. We proposed FENT, which is a contrastive learning-based long-tail trajectory prediction framework. In this paper, we put forward a feature-enhanced cluster-based contrastive learning to recognize tail trajectory patterns and form a feature space with separate pattern clusters. Furthermore, a distribution-aware hyperpredictor is brought up to better utilize the shaped feature space. Our proposed method is a model-agnostic framework and can be plugged into many well-known baselines. Experimental results show that our FENT outperforms the state-of-the-art long-tail prediction method on tailed samples, while maintaining or slightly improving the averaged performance. Long-tail trajectory is a safety-critical topic in autonomous driving scenarios, but have been rarely discussed. Despite the high accuracy that the advanced prediction methods have achieved, most of them treat the samples in the datasets equally in both training and evaluation phases. However, in the real-world scenario, most trajectories follow simple motion patterns like constant velocity, while complicated and highly interactive patterns are hard to collect. This results in the long-tailed phenomenon in prevalent datasets. Those hard samples are with various different motion patterns, and they often suffer from larger prediction errors, which makes them more safety-critical. We can see from the left figure about the long-tail prediction error distribution, the easy head patterns, and the hard-tail patterns of the ETHUSY dataset. Mackenzie et al. Recognized the hard-tail samples with Kalman filter prediction errors, and used contrastive learning to adjust the trajectory feature embedding space in their work. There are mainly two flaws of their method. Firstly, they push all the hard-tail samples together in the trajectory embedding space. But hard samples are with various different patterns and should be treated differently. Secondly, the Kalman filter predictor have weak predictive ability, therefore cannot reveal the hard samples with respect to the neural network predictor. In our work, we propose a feature-enhanced contrastive feature learning for long-tailed trajectory prediction. Instead of Kalman errors, we use pattern clustering with future trajectory information to recognize the samples with hard patterns, which does not depend on the predictor. Also, instead of pushing all the hard samples together, we separately treat different patterns according to the cluster prototype. We propose a distribution-aware hyperpredictor, aiming at providing separated decoder parameters for trajectory inputs with different patterns. Specifically, we use another hypernetwork to generate the decoder weight. Our method achieves outstanding performances. This figure illustrates the overview of our method. The red modules are our FENT modules, while the blue modules are the baseline modules. Our method mainly contains three parts: feature-enhanced clustering, prototypical contrastive learning, and hyperdecoding. We use 1D-CNN and LSTM to extract past and future trajectory features and cluster according to them. Then we use the pseudo-labels obtained from clustering to perform prototypical contrastive learning and optimize the feature embedding space. Then we decode the trajectory with a hypernetwork determining different weights of the decoder for different samples. PCL is a kind of contrastive learning method. Given pseudo-cluster labels, PCL can pull the features of instances belonging to the same cluster together and push the features of instances in different clusters apart, as what vanilla contrastive learning does to the positive and negative samples. We do PCL on the features at the bottleneck of the trajectory prediction network. The PCL loss has an instance-wise term to help the instances gather together faster, and an instance prototype term help preserving local smoothness and the formation of clusters with different patterns. The PCL loss works as an auxiliary loss. Hypernetwork is an approach of using a small network, which is known as a hypernetwork, to generate the weights of the main network. The hypernetwork outputs separate decoder parameters for head and tail clusters, which make the decoder aware of the distribution of the clustered feature space. The formulation of hyper-LSTM is in the box below. The feature embedding Vs determine the Zs, and the Zs determine the Ds and Bs, therefore adjust the weight for the LSTM. We apply our method on two famous trajectory prediction baselines, Trajectron++ and YNet, on ETHUSY, Nesines and SDD. Experimental results shows that our method can outperform state-of-the-art long-tail prediction methods on the tail samples, while maintaining or slightly improving the overall performance. Those figures show the qualitative visualization results. The left figure contains cases with some rare social interactions, such as collision avoidance, parallel walking, and crowd avoidance. We can see our method perform well on those non-trivial cases, thanks to our proposed module for optimizing the embedding space and the decoder. The right figure shows results of our different model variants, and it can be seen that our full-fent model performs the best. We might take a look at the SNE results of the shaped embedding space. We can see from the figure that our future enhanced PCL method on the right can decently separate the tail patterns and the head patterns, which outperforms the baseline on the left. Also, we can see that our method can form different clusters for different tailed patterns, while in the feature space of Mackenzie-Ito in the middle, all the samples of the three tail patterns are pushed together. That gives our method a higher performance. To conclude, we propose a feature space shaping method and a hyperdecoder for long-tailed trajectory prediction. Experiment results show that our method can outperform state-of-the-art long-tail prediction methods. Also, our method can be plugged into many strong prediction networks. Thank you all for listening and wish you all a good day.